Let's learn another way of finding maxes and mins of a function. And this is for functions where we're not bounding it by a and b. So it's a function that potentially spans all x's. There might be places where it's not continuous, but for the places where the function is continuous, here's another way, or a way, an important way, a named way of figuring out where the maxes and mins are. So you might want to stop and take these notes for a bit, but I'll just talk about them. For example, if we have functions defined outside of any interval, so there's no boundaries like we had last time, how do we find the maximum and minimum points? So remember what we had before. We had some critical values, we had the endpoints, we just checked the value of all of them, and we found the largest and the smallest. But what if there are several largest and smallest? How do we do that? Two, sometimes we can't graph a function. Maybe it's not graphable, or maybe we're on the AP exam and we can't graph, or maybe we want to write a computer program to find the max and the min, and the computer program doesn't know how to read a graph. It just knows functions. So how do we do that? And basically, who really cares anyway where the max and min is anyway? You know, nobody cares, right? Well, people do care. People want to find the best or the least, or the biggest or the smallest of things, like the fastest engine, or the most profit, or the worst time. Not the worst time like in high school, but maybe the worst time, so something took the longest amount of time, maybe sometimes that's worst, or maybe sometimes something lasted the shortest amount of time. Maybe a shortest distance of something. Like I have projectiles, and I have an equation that defines them, so what kind of values would give me the shortest distance. So these are ways that people might care about a max or a min. Now, listen very carefully, and you can write this down in your notes. We eventually are not going to refer to graphs, but I want to show you sort of why what we will do sort of makes sense. So we're going to look at graphs, but ultimately we are not going to graph. Okay, so let's see if I can get this all on here. I think I can. Yeah, and I need my math tool. Hello, math tool. Okay, so can you stop the video and take a picture? Take a picture with your pen and pencil of this graph. Notice I'm very picky. I would like this min to be shorter than that min, to be shorter than that max, to be shorter than that max. So take a picture of that, or draw a picture. Oh my goodness, I'm hangry. Okay, and then before we see anything, I just want you to sort of observe. You know, you can take notes, but then come back and listen to me. I've broken up the x values into things left of A, at A, between A and B, at B, between B and C, at C, etc. So that's what that top part means. And then I just want to observe the function behavior. So you can see it's decreasing or increasing or flat, whatnot. And then I want you to think about what the derivative is doing at those points. We've sort of talked about this already. And that's flat. This is just a mistake there. Woo, white out. I was going to say 0, but that's what I want to say down here. So the behavior is that it's flat or constant at that value. Okay? And shockingly enough, you'll see some sort of connection here. And for what's going to come in the future, think about, you know, I have my tangent line. So if a function is decreasing from left to right, then the slope of the tangent line is negative. So the rate of change is negative. So the y value is decreasing as x is increasing, etc. So take that picture. Oh my goodness, how many times am I going to say that? And then I will start the next video now.